Okay, this video is going to be about the Fibonacci number sequence, and the Fibonacci number sequence is generally discussed when talking about the concept of recursion in computer science. Now, recursion is when you call a function inside of that same function's definition. Okay, and so we're going to get into the specifics of that. I have the Fibonacci number page open in Wikipedia, and I wanted to take a minute to express how wonderful of a website Wikipedia is. I always try to donate to them whenever they ask for donations because they have excellent material. Science, technology, engineering, math articles are phenomenal, scholarly articles, and it's all free, and there's no ads either. So if you have the means, please go ahead and donate to this wonderful website. Just a little plug for them because they do great work. So anyway, back to Fibonacci numbers. Okay, here we have the Fibonacci number sequence. So it starts out with basically two given cases. So for Fibonacci number 0, the value is 0, and for the first Fibonacci number 1, the value is 1. Okay, so if this is a function, we would say f of 0, the resulting value would be 0, and here f of 1, the resulting value is 1. For all other values of n greater than these two, right, greater than 0 or greater than 1, so that would be 2, 3, 4, 5, 6, on up to infinity, the definition of that Fibonacci number is f of n equals f of n minus 1 plus f of n minus 2, right? Or you could switch these around. The point is, it's the last two numbers in the sequence, okay? So if 0 and 1 are given, so this is the first several numbers of the sequence. 0 and 1 are given, so the Fibonacci number n, where n equals 2, you say 2 minus 1, that's this value, plus 2 minus 2, that's this value. So you add those last two together, and so the value is 1. And that is for n equal 2. This is for n equal 3. You add up the last two items. For n equal 4, you add up the last two items. 1 plus 2 equals 3. N equal 5, add the last two items. Okay, so for any value of n, you would add the Fibonacci number n minus 1 plus the Fibonacci number n minus 2. Okay, so this definition lends itself to recursion. And again, recursion is the concept of calling a function inside its own definition. Okay, so let's take a stab at just coding this up the way they have it here using recursion. And we're going to point out some potential shortcomings and issues when you actually try to code this up with a computer as opposed to just looking at it mathematically. All right, so we're going to have a new file here, and we're going to call this Fib Recursion, but we're going to call this bad because this is going to wind up being pretty inefficient. And we're going to explore what that means. All right, so let's start by defining the Fibonacci sequence. Oops. There we go. Fibonacci, and we take in some n value, right? So if the n value is equal to 0, then that we return 0, right? Because if we go back to our definition, these two cases are given. If the n value is 0, return 0. If the n value is 1, return 1. And if it's anything greater than that, we have to do some sort of calculation. All right, so if n equals 0, or n equals 1, we can just return n. Okay, so this is sort of a shortcut. If n is 0, then we return 0. If n is 1, then we're returning 1. Right, so that satisfies our two base cases. If you have any experience with recursion, it's very important to note when you define a recursive function, you always have to have some sort of base case that ends the recursion. Right, so this base case is when we stop recursing and then start going back into all of the functions that called Fibonacci recursively, right? So this is the base case, and if this isn't true, if we have an n value bigger than this, then we simply need to return, as they defined it, Fibonacci. See, they defined it as n minus 1 plus Fibonacci n minus 2. Right, so it's going to be the last 2 items. Let's take a second to understand what this code is going to be doing. If I call Fibonacci of 0, right? We come in here, I'm passing in the argument 0. That means this parameter in is going to store 0 when I call this function. Then is in equal to 0? Yes. So it just returns 0. All right. What if I had Fibonacci 1? So 1 is the argument. It's stored in the parameter in equals 1, so we return 1. Okay, so we satisfied those 2 base cases. What if we do in equals 2? All right, so 2 is stored in our parameter in. This is false, so we move down here. And now we reach the part of the code that actually invokes the recursion. All right, so in order to calculate the Fibonacci number of n equals 2, we have to calculate the 2 previous ones. So we call Fibonacci with n minus 1, which would be 1, right? Because currently n is 2. So that would take us back to this base case. So this should return 1. And then we would call Fibonacci of n minus 2. Now remember, we called Fibonacci with 2. So this should be 2 minus 2, which is 0. So when that calls, we're actually going to enter and get this base case. So the result here should be 1 plus 0, which should be 1. All right? And so then we can call it with 3 and see what happens. This one starts to get complicated, right? And I'm going to switch these around, Fibonacci n minus 1 and Fibonacci n minus 2, just because I have an image later that I'm going to be showing, and it's in this order. But obviously if you add 2 things together, it doesn't matter which one you add first. This just matches the image I'm going to show. So here we have Fibonacci 3. We have an n value of 3, right? So we're not in this case. So what we need to do to calculate Fibonacci number 3 is get Fibonacci number 1 and Fibonacci number 2 and add them together. Well, Fibonacci number 1 is 1, and Fibonacci number 2, we're going to have to recurse again and get the sum of Fibonacci 0 and Fibonacci 1, right? So this is the concept of recursion. It's a sort of elegant way to do a loop, right? And if you don't know anything about recursion, you might want to watch a video or 2 on recursion before going too much further. But it's relatively simple. It's sort of a way of looping with a function call inside of its own definition. You can also have a sort of recursive effect by having 2 functions and each function calling the other one inside their definitions and that sort of thing. All right, so let's take a look at what the result is here. Let's just print out some of these function calls. We'll say for I in range 35, we're going to print out the result of, I'm going to use a formatting string here. So the result of Fibonacci, and I'm going to call it with the argument I. That result is going to be, and here I'm actually going to call the function. All right, so this is just labeling our output, Fibonacci, and then the I value. And then here we're actually calling the function with the I value. All right, so when we run this, we'll take a look at what's happening here. 3, this is Fibonacci recursion bad. So it goes through and starts printing these out, and you see it slows down tremendously. All right, see how slow that last one was? Number 34. These first several went lightning quick, right? And we can double check and we can verify if this is the correct sequence. So we got 0, 1, 1, 2, 3, 5, 8, 13. Let's see, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 21, 34, 55, 89, 144. Yeah, so it looks like we're doing this correctly, but this seems very inefficient, right? What if we increase this to, 40 or something like that? Like, is that, how long is this going to take? Now we know, just looking at this problem, it should be relatively simple. You're just adding the last 2 numbers, and if you don't have that number, then you add the 2 before it. right? But the way we've coded this up, it seems like it's taking an extraordinarily long time. You see how long 35 took? And then 36 is even longer. And here on my computer, I have 8 CPU cores, and I have them graphing out their output right now. And one of them is just pegged all the way 100% because it's crunching so much data. This shouldn't be that difficult of a calculation, right? So this ties into efficiency, the concept of efficiency. How you code something matters, because this is a relatively simple calculation. Any one of us could calculate by hand the Fibonacci sequence of n equals 38, right? It would take a little while. We'd have to add some numbers together, but it really wouldn't be that too awfully bad, right? So we need to look into why this is happening, and it has everything to do with the way we are using recursion here. And the primary reason that it's an issue is because we are calling, we're making 2 recursive calls in one function definition. Okay, so it finally completed over here. Now let's take a look at why this is the case. All right, so let's see if I can. I'll actually open this up, make it full screen. All right, so this is an image demonstrating an inefficient Fibonacci recursive algorithm, right? This is the algorithm we just coded in. If n equals 0 or n equals 1, return n. Otherwise, return n minus 2 plus n minus 1. And then we're calling, this is a graph of what happens in Fibonacci n equals 6. All right, so our givens, the Fibonacci number 0 is 0, Fibonacci number 1 is 1, and this is the graph of case n equals 6, or in other words, f of 6, and the resulting value is 8. Okay, so what happens in our code, right? So if we call f of 6, right, the next thing we have to do, this is false, these are false, so we have to make 2 other calls to Fibonacci. So we have to call f of n minus 2, so if n is 6, that's going to be f of 4, and then f of n minus 1, that's f of 5. Okay, now to satisfy, to get the Fibonacci numbers from these calls, right? These are also recursive. Okay, so let's look at Fibonacci n minus 2, right? If n is 6, this is 4, so we need Fibonacci number n minus 4. We have to subtract 2 and then subtract 1, right? So if this is 4, this would be, this would be 2, and then this would be 3. And then this one we have to recurse again, right? This is Fibonacci 2, so we need Fibonacci number 0 and Fibonacci number 1, right? You see how each one of these calls is calling Fibonacci again. Now the problem comes with repetition. So I've color-coded each one of these. So the f of 6 is gray. The f of 5, Fibonacci number 5 function call, is blue. And then the Fibonacci f of 4 is green. And we see there's a duplicate here. And actually, the whole tree underneath each one of these green f of 4s is the same tree. We're doing the same amount of work. If we calculate the Fibonacci number here, 3, or the Fibonacci number here, we shouldn't need to calculate it again here because we should have it. We should save that data and use it over here instead of having to calculate it all again. And if you go down, you see all of the leaves of this tree. This is a binary tree here. All of the leaves here are either 0 or 1. Those are our given cases. F of 0 equals 0, f of 1 equals 1. So in this case, f of n minus 6, remember we said n is 6, so 6 minus 6, this is f of 0, Fibonacci number 0 is 0. 6 minus 5 is 1, so this is Fibonacci 1, and the resulting value is 1. And here this is Fibonacci number 6 minus 4 is 2, so the second Fibonacci number, right? Or the second index, the indexing starts at 0, right? So that's the number 1. You add 0 and 1 together and you get 1, right? And then this one, we see we basically add Fibonacci n minus 4, which is the Fibonacci 2 number, f2, plus f1, which is 1. So add those together, 1 plus 1 is 2, and 1 plus 2 is 3, and the 3 plus 5 is 8, right? But the whole problem of why our program runs slowly, this is only going to n equals 6. How many additional calculations do we have? You know, we shouldn't need that many. If we are smart about how we are keeping track of this, we can reuse the calculation. If I know that f of n minus 2, so that's f of 4, if I know that the value there is 3, I should be able to reuse that over here, right? Once I calculate it one time, I shouldn't ever have to calculate it the same way again using recursion all the way to the bottom. This is highly inefficient. This is an exponential growth problem. So despite the Fibonacci sequence being defined in this recursive way, when you actually code it that way, you still get the correct result. However, the way the computer calculates the result is very, very, very inefficient. Okay, so there is a way we can code this efficiently using recursion, and I'm also going to show you an example of how to code this just in a loop. So anything you code with recursion can technically be converted to a non-recursive form using some type of loop, but sometimes it is complicated to do that. It's not always obvious. So recursion kind of gives us an elegant way to loop over some things in different situations that might be harder to express with loops. All right, so I'm going to minimize that and go back to our code. So this was the bad version of the Fibonacci sequence. Okay, so one other thing we can do here is we can take a look at how much work is being done. All right, so what do I mean by work? Well, I'm going to just add a variable in here and keep track of the amount of work we're doing. All right, so I can say work equals none. And what I want to do is I want to make sure every single time I call Fibonacci, I'm getting the amount of work to calculate that number starting from scratch. Okay, so I can put a work variable here and start it at 0, and then each time this function is called, I can say first I'm going to be modifying this global variable, so I have to use the keyword global and tell Python that I'm modifying a global variable, not a function scope variable. So then I'm going to, each time I enter this function, I'm going to add 1. So this is an example of keeping track of an abstract form of work, right? How much computing processor does this take? So we're trying to compare one algorithm to another. So we're trying to be as generic as possible. Obviously, just accessing, like checking for equality might be a certain amount of work. Calling a function might be a certain amount of work. Incrementing data might be a certain amount of work. We're trying to abstract all that and just get a general sense of which algorithm is better, right? So that's where we use this work. And so we start work at 0. Anytime we call this function, we add 1 to our work. And then we're going to print out the work for each one of these. All right. Now there's a problem here because we're looping over this. So every time we call Fibonacci, it will add work from the last time, right? So work is defined as 0 outside the scope of the function. Then every time I call it, it adds work. So if I call Fibonacci 40, there will already be a whole bunch of work stored there. So I want to avoid that. So what I have to use here is a wrapper function, right? So I need to say something like, I'll start out work as none, and I'll define this wrapper. There we go. So I'll call this the wrapper fib. And this function is basically just going to call Fibonacci, right? So it's going to take a value in as well, but what this is going to do is it's going to call global work. So we're going to access the global variable work, but we're going to set it equal to none. I cannot type right now, sorry about that. All right, so work equals 0. So this just allows us to reset the work every single time, and then we'll just go ahead and call Fibonacci and then pass in the in value. So this is just a little wrapper function around the actual first Fibonacci call. All right, and all we're doing is setting work back to 0 each time. Okay, and so what we need to do down here then is, instead of calling Fibonacci directly, we just need to call the wrapper fib. And again, this is just to demonstrate the amount of work that's being done in each one of these function calls. All right, so I want to see that work, obviously. So down here, when I print out this information, I get the Fibonacci number, but then I also want to see the amount of work. All right, and so I'll print out how much work was done in the last Fibonacci function call. All right, so let's take a look at running this. We already saw it goes very, very slow. Let's put this back down to 35, so that way it doesn't take so much time to run. I'll run this again. So look how many units of work are taking place. This is 11 million, right? 18 million units of work. All right, and we arbitrarily defined what work means, but it's essentially one function call anytime we called function Fibonacci. So that function was called that many times, when really a human could easily sit down and calculate that. It might take them a while, but it's doable, right? So this is an extraordinarily inefficient algorithm, exponential. Right? So what we want to do is we want to think about what that would mean to make a good version of this. All right. So let's make a new file, and we're going to call this Fibonacci Recursion. But this is the good one or efficient one, and it's going to be a little bit more complicated. But how you code things is very important. It gives you that efficiency gain that you get can be a major advantage to anything you're doing, especially when you start talking about multiple users using your code. If one person is using this bad algorithm for Fibonacci's number sequence, that's bad. But if a million people are, that's even worse, right? So it's very, very important to think about. All right, so here's a good version. Let's think about what it would mean to make a Fibonacci recursive function, and we're going to try to make it efficient. Okay, so we need to keep track of in still, but what we want to do really is we want to only calculate, only want to have one recursive function call per iteration, right? So we have to think about how we can make, the problem with the bad Fibonacci is we're calling it twice. So for every single Fibonacci call, you call two more, and each one of those calls two more, and each one of those calls two more. So that's exponential by definition, right? So we only ever want one recursive function call in our recursive functions definition, right? So we want to think of maybe keeping track of how many times we're going to start with the base cases 0 and 1, and then we're going to use those to get to the third one, and we're going to use those to get to the fourth one. So we're going to instead of starting from the ending case, like here we started from in and then went back in -2 -1 and then went back further. So we're sort of starting at the end and going to the beginning. Here in this version we're going to start at the beginning and go to the end. All right. So I'm going to need some other things up here, but we'll just start with Fibonacci In. And I will start again with, if in equals 0 or in equals 1, then we're just going to return in. All right, but if not, then we need to calculate the new Fibonacci number. All right, so the new Fibonacci number is going to be our in value, right? So if we're going the other direction, we need to keep track of that. So what iteration, what I value are we on? If n is 0, we return 0. If n is 1, we return 1. And in the case that n is 2, we would be on the second iteration, right? So if n is anything above 1, we're going to be moving into this code here, right? So this new Fibonacci number is going to equal the sum of the last two. Well, we probably need to pass those into our recursive function. Okay, so this would be the Fibonacci number, let's see, Fibonacci of n minus 2, and if it's the second iteration, right, n minus 2, so 2 minus 2 is 0, right, and then the Fibonacci number n minus 1, and we'll set a default value there for that as well. And the default value, if this is the second iteration, right, it could start with 0 or 1, and if this iteration is the second iteration, then n minus 1 would be 1, right? So these are the default cases, and we actually only ever use these in the recursive call. So whenever we call Fibonacci, we're just going to supply the n value, but when we call Fibonacci recursively, we're going to set these new values. All right, so what do we mean here? So the new Fibonacci number is the one we haven't calculated yet. Remember, we're starting from Fibonacci 0, then going to Fibonacci 1, then 2, then 3, then 4, then 5, right? So there's always going to be a new one, and we're going to be keeping track of the last two Fibonacci numbers we've calculated, because that's all you need to calculate the next number. You just need the last two. So in every recursive function call, we're going to keep track of the last two, and then we can use them to add and get the new Fibonacci number if we need to, right? So we get a new Fibonacci number here, and how do we calculate that? Well, if these two were provided to us, that is Fibonacci n minus 1 and Fibonacci n minus 2, we just add those together, right? N minus 2 plus Fibonacci n minus 1. All right, so this new fib we have, and we want to basically check to see if the iteration we're on, so remember the iteration we're on is basically the Fibonacci number we've calculated so far. We've started calculating at 0, Fibonacci 0. If we go back here, this is Fibonacci 0, Fibonacci 1, Fibonacci 2, 3, 4. So the I is what iteration we're on. Each time we go through, we're passing in the last two numbers into our next recursive function call, right? And then the I value has to go up because it's the next iteration. And then we pass in the last two numbers into the next iteration, the last two numbers into the next iteration. That's what we're trying to do here. So at I equals 2, the previous two Fibonacci numbers are 0 and 1. Okay, so we can add those together since we have them as 0 and 1, and so the new fib is 1. And we can check to see if I is equal to n. Okay, so if the iteration we're on, if we finally iterated all the way up to the nth Fibonacci number, n, right, then we have the Fibonacci number we're looking for. We just return it, new fib. So we need to return that value. All right, and if I is not n, then we need to calculate the next Fibonacci, right? So we calculate the next Fibonacci number. The end point, our goal is still n. We're always trying to calculate the nth value. But the I value we're passing in now is I plus 1. We're on the next iteration, right? And then what do we pass in for fib minus 2, or fib n minus 2 and fib n minus 1? Well, fib n minus 1 now becomes fib n minus 2, right? And then new fib becomes fib n minus 1, right? Because new fib is going to be the last calculated Fibonacci number, right? So this one's quite a bit more complicated of a design. We have to pass in more variables, but the key thing that we're trying to do is boil this down in such a way that we only have one recursive function call. Otherwise, we're going to get an exponential explosion, and our algorithm is going to be very, very inefficient, right? So let's take a look at this and see what kind of result we get here. and we want to look at the speed again, right? So let's look into adding some work. So if I have work equals 0, I'm going to need to do the same thing here. I'm going to need a little wrapper function. I'll say define wrapper fib, be pass in the in, and I can say global work equals 0, and then call Fibonacci itself and pass in. Okay, so again, this just ensures that we reset work each time we call it, because we're trying to compare these two algorithms. All right, so to save time, I'm just going to copy and paste what we had from our bad algorithm and put it back into this good algorithm here. All right, so we're going to go to 35. We're going to call wrapper fib with I, and we should have some amount of work. Last thing we need to do is somewhere in this Fibonacci function we need to call work. So let's say global work and work plus equals 1. So we add 1 to work each time we call the function. So this should give us a sense of the differences between these two. So we want to call the good version here. And you see how quickly that went and how little work it took for each one of these. So algorithm design is incredibly important. Compare 33 to this number, 18,500,000 about. Or you could do it in 33 units of work. Okay? So hopefully this shows you the importance of algorithm design, why it's important to think about how your algorithm operates, why the number of loops that are executed is important to know. It's very, very important stuff, especially at scale when lots of people are using your software. All right. So we'll do one more quick example of a way to convert this recursive algorithm into just a basic looping algorithm. And for this particular case, it's not too difficult. All right. So we need to create a new file. And we're going to call this, let's see, this is fib loop. And this one is good as well. So this one is efficient. .py. All right, so we can say we're going to need this work situation, and we're going to define our algorithm. We have an in value. Now this one is a little bit easier to define. So what we're going to do is we're going to start out with fibs, which is a list of Fibonacci numbers, and they start out at 0 and 1 because those are the two Fibonacci numbers that we are aware of, right? We're also going to go ahead and track the work, and I'll say the first time through work, you add work equals 1. Okay, so it takes the first, this is being called one time, and so we're setting work equal to 1 to start with because we don't have a wrapper function or anything. So work equals 1, and then we're going to go in a loop, and we're going to say as long as the length of our list of fibs is less than our in value, then we need to calculate the next Fibonacci number, right? Now let's see, is this completely correct? The length of fibs. So here, this is Fibonacci number 0, this is number 1. So the length of fibs is 2. If the length of fibs is less than n, right, is 2 less than n, let's say we're calculating 2, right? Is 2 less than n? No, it's not. So that means we're off by 1 here. Right? So we're going to do some stuff in here, but when we get done, we basically just return fibs and then that in value, right? So the reason I added this -1 here is let's examine the case where n is 2. Right? So we're calculating n is 2. So the length of our list starts out at 2. If we don't have this -1 in there, is 2 less than n? And n is 2. So no, 2 is not less than 2. So we'd skip over here. Then we try to access the second index item. Well, this is index item 0, index item 1, and the second index item is beyond the bounds of the scope. So that's why we need to subtract 1 here. Okay, it's basically because indexing starts at 0. So it's very common to subtract 1 in lots of cases when dealing with arrays, especially when you have the length of something. All right, so the length of your list minus 1, if that is less than n, and remember we're trying to find the nth Fibonacci number, so if it's less than n, we haven't calculated yet, so we need to calculate the next one, right? So how do we do that? Well, again, we need a new Fibonacci number. New fib. This is going to equal fibs, and we're going to take the second to last Fibonacci number. So that in Python, it's nice, you can use negative indexing. And then here we can say plus and take the last Fibonacci number. So we're adding the last 2 Fibonacci numbers there. Then we can just add that number to fibs. Right? And then each time through this loop, we're going to consider that a unit of work, because we're basically doing the same thing we were doing in the recursive function calls. Right? Each time through the recursive function call, we would calculate a new Fibonacci number. Right? So here we're going to say work plus equals 1. And this, again, is just so we can kind of compare the algorithms. It's not a perfect comparison, but it gives us an idea of what's happening. All right. So this is all occurring in a loop. And so we're checking to see if the length of our list of fibs is long enough that we can access the nth index of 1, right? Once this becomes true, that means there's going to be an nth index in our list of Fibonacci numbers, which will be the nth Fibonacci numbers. So as soon as we break out of this loop, then we just return fibs, the element at index n of our fibs list. And again, we do the same thing. I'm going to copy this from one of these. There we go. Oh, forgot my colon here there. All right, so that looks good. So we're going to run this. And again, you see there's no recursive function call. This is all a loop-based algorithm. All right, so we've converted the recursive algorithm to a loop-based algorithm. And let's see if this one is efficient. Wrapper fib. Oh, there is no wrapper fib, so I have to put in the actual Fibonacci. All right. And you see we still get the Fibonacci numbers. And you see the work is similar to the work from the recursive algorithm that was efficient. Okay, so this is just basically to showcase there are different ways to code things, many different ways to solve problems, but the way that you code things does matter. It's very important. It saves CPU cycles. CPU cycles are generated by electricity, and it actually, winds up making. You can save money on electricity, but you can also save the planet as far as, green energy. Like, there's no need to waste that kind of energy to make this calculation. So the more efficient we can be, even with calculations, we can save money and energy and be green and help the planet and help everybody. Not to mention the human waste that comes from an inefficient algorithm. As I said, if 100,000 people are using this, they're all waiting however long it took. What did it take? 30 seconds for that to run. That's 100,000 people times 30 seconds. So that's a lot of human time wasted, which is another resource to manage. So a lot of these efficiency algorithms that we talk about, it's all about resource management. And one final thing I want to say on this Fibonacci loop, there is another resource that is expanding in this version. Okay, so with Fibonacci, the way we did this in this loop, we're keeping track of this list of numbers here, right? And then we're adding to it, and we're adding to it, and we're adding to it. If I wanted to get a very, very large Fibonacci number here, the problem is I'm keeping track of all of the Fibonacci numbers. So if I go too high, this is a graph of my RAM on my computer, If I try to make a calculation with my Fibonacci numbers that's way too high, this will skyrocket because I'm keeping track of all of the previous Fibonacci numbers, and I don't really need to, right? So here, what we could do is when we add one, we'd remove the other ones because we don't need them anymore. And this would be a memory management issue. This would be a memory efficiency type of change. So there's all sorts of efficiencies you need to be concerned with, and depending on how your algorithm is being used, you need to be concerned with different types of efficiencies. All right. So hopefully this helps you start to understand the importance of efficiency, how you code matters, and a little bit about recursion. All right. So hopefully you learned something, and that's enough for this video.